Then let's start, and I would like to talk about real-world video AI. And before going there, I first want to highlight some recent achievements of the area. So here you see a video where people have tried to classify the action, the activity that is happening in the content. So on the top in green, you see the most likely activity given the pixels, right? And as you can tell, it is pretty good. So even very exotic activities like hurling or freestyle slalom skating, the model can recognize quite accurately. And this is work from folks at Facebook. Here's another example again from Facebook, Christoph Weichtenhofer et al. And here they show not only the recognition of the activity, but also recognizing the box around the actor performing the activity. And again, this is an amazing progress. I mean, if you had asked me what the field would look like when I started more than 20 years ago, I could have only dreamed that this would have been possible. Here's another example, actually worked from my own lab in Amsterdam. And here the goal was to, given the sentence, woman in a purple dress running, identify the pixels in the video that belong to this actor and action. Now, it is not perfect, but it does a reasonable job already to find the pixels based on the sentence. And the beauty of this algorithm is not the precision of the pixels, because it's not so precise, but the beauty is in when you change the sentence. So now the sentence is gray dog running on a leash during a dog show. The algorithm is clever enough to identify the pixels that sort of belong to the relevant dog. And this is not so simple as it may seem, because there are many other dogs also in the background, because this is a dog show event. And the algorithm has figured out how to identify that dog that is running. So that is actually quite nice. Here's another example where we look into group activities. So here we are not only interested in identifying the class labels of actors moving or setting up or falling, but we also use the configuration of individual actions and actors to identify the group activity, which in this case is called a left set in a volleyball match. And here's a most recent example of a forthcoming ICV paper where we looked into video relation detection. Somehow the video is not playing accurately on my screen, but what it's supposed to show is a bounding box around the subject and an object. So in this case, the adult, and the subject, the horse. And then it also detects the relationship between the two. So in this case, it recognizes that the adult is cleaning the horse, and it is following the boxes throughout the video. So what can we say of what we have achieved? So if we look into generalizing over many methods that have appeared recently, we can say that if you have a sort of a closed world assumption where you have plenty of labeled data available, you can do pretty nice things with deep learning. And essentially, you can get state-of-the-art results and show the potential of the approach on many problems that you can think of. Now, it is tempting to move into this direction as we progress. So we slowly open up our world, and we change the distributions of the data sets that we see during training to really come to a real world video understanding, so to say. But there is a problem, which I would like to refer to as the video understanding paradox. And the paradox here is that as the understanding becomes more and more specific or realistic, it is unrealistic to assume that sufficient examples to learn from will be commonly available. So here is an example of an event that may happen in Amsterdam, quite often actually, where somebody is walking around on the city streets with a crowbar, finds a bike he likes, breaks the lock, and cycles away. Now, you can imagine building a bike stealing detector, right? The problem is that you won't find many instances of video footage where this event actually happens, because the burglar does not want to be caught and does not want to be caught on camera. So finding sufficient examples and labeling them will be very problematic. Not to mention identifying sufficient bounding boxes of the subject with enough diversity, or finding all the pixels of burglars stealing bikes. And of course also causal inference. So the fact that somebody is walking around on the city with a crowbar is maybe suspicious, but it does not necessarily imply that the person wants to steal a bike. So for all these reasons, I believe that continuing in the same way as we have been doing so far is a dead end and will not bring us to a real world video AI. So the mission of my lab is essentially to move into this direction. So get into real world video AI with as little as possible dependence on supervision. Now, how to get there? Luckily, there's a lot of tools and frameworks from machine learning that come to the rescue. So one of the very popular topics is self-supervised learning, where the trick is to learn from a hidden structure in your data to pre-train your model so that you need less examples for downstream tasks. So one of such tasks is rotation prediction, which you can create artificial rotations from your data, and then you learn a network, or you train a network that learns to predict the right orientation. And because you know the rotation that you have performed, you also have a rotation label, and in this way you can train a very reliable backbone. Another approach is self-training. It resembles the self-supervision to some extent, but rather than relying on artificial labels or pretext tasks, it relies on pseudo-labels that are obtained from clustering assignments. So you cluster your data, and the cluster centers become the pseudo-labels. Now, this has been proven effective in transfer learning, especially for large-scale target data sets. So you train on a huge amount of weakly labeled data, assign pseudo-labels after clustering, and then fine-tune the model on large-scale kinetics dataset, for example. Another approach is meta-learning. So here you create all kinds of small batches of training and test sets at training time, so to say, and you learn how to solve a few-shot classification problem or a domain generalization problem. Very effective approach. It does come with a downside because you need many train and test sets at training time. So you still need a lot of data and a lot of labels. Another popular set of techniques relates to domain generalization. And here the problem is to learn from a set of scene or source domains. Like here in the example, you have photos, art paintings, and cartoons of your favorite animals. And then the problem statement is, how can you recognize these animals in an unseen target domain? So the target domain in this case is sketch. You haven't seen any sketches during training. And how can you still predict the right label under this problem? Then there's a combination of these problems, like few-shot domain generalization, and this actually worked from my team that appeared at iClear this year, where we sort of combine meta-learning for the few-shot setting and also learn to generalize to unseen domains using a new form of batch normalization. Okay. So this is where we are, and what will be the topic of my talk today. I would like to talk about the value of similarity, and I will present 3 very recent works from my lab that try to reach real-world video AI someday and take the first baby steps, so to say. So the talk will cover 3 types of similarity. The first one is motion similarity, the second one is audio-visual similarity, and the third one is spatiotemporal similarity. That also, all 3 come natural with the video medium. This is work that is to appear in ICV next month. joint work with Kirill Gavrilyuk, PhD student in my team, and two colleagues from Qualcomm AI research, Mihir Jain and Ilya Karmanov. So here we look into self-training. So recall that self-training relies on pseudo-labels that are obtained after clustering. So the goal then becomes to predict those pseudo-labels. Now, quite some papers have appeared in the literature that have demonstrated that this is a very effective approach to transfer appearance models for large-scale target data sets. But we have a different goal in this work. And our goal is can we self-train a model that can be effectively fine-tuned, not only on large-scale video datasets, but small-scale video datasets with around 10,000 videos. So this setting is much more closer to a practitioner setting. So unless you are Facebook, Google, or Amazon, where you have huge amounts of video at your disposal and huge amounts of compute, for practical use cases, most of the time, the video dataset will be rather small scale and compute is actually a problem. Now, it is well known that for small scale video datasets, appearance is not so descriptive. It is much more reliable to rely on the motion features, on the optical flow representation. The downside of optical flow is that it requires an additional computation step. So in addition to the pixels, you need to pre-compute optical flow, and then you can do your recognition. So what we strive to achieve is to train a network in a self-training fashion using optical flow, but we want to avoid optical flow computation during inference. And we are inspired by this notion of generalized distillation, and especially this work of Crasto et al. That appeared at CFPR 2019, where they have sort of like a student-teacher, teacher-student approach, where the teacher computes the optical flow, and the student no longer needs to compute the flow because it has learned to extract RGB frames in such a way that it sort of like augments the optical flow. It does so by using the flow features as privileged information during training. The downside of this approach is that for the training, they still require a large-scale labeled video dataset. So typically people rely on kinetics or one of its variants with a huge amount of labeled data. Now, we are interested in reaching the same goal but without these large-scale labeled video. And basically, our main contribution is a model that we call motion fit. And this is a motion augmented self-training procedure. Motion fit can transfer flow to an RGB model using self-training on unlabeled video data. And this is the key novelty approach. So we are the first to use motion augmentation in a self-training fashion, and we no longer need unlabeled video data to get there. In addition, we have performed an extensive empirical study to basically discover how to form these video pseudo-labels at a smaller scale, and I will highlight some of these empirical findings as well. So how does the motion fit model work? Well, at first, it starts to train what we call a motion pseudo-label generator. So given a data set, it extracts a motion representation using optical flow. It trains a model based on this optical flow using some small amount of class labels. And in addition, we also introduce a multi-clip loss that simply samples multiple clips per video and averages those using the cross entropy. The advantage of having multiple clips per video is that it better preserves the temporal information and to make sure that at least one of the clips really captures the foreground motion. So you have the relevant information in a condensed time window, so that is you will get a better backpropagation and better representation learning. The second step is the motion augmented self-training. So here it becomes interesting because from a given source dataset, let's say kinetics 400, we extract the optical flow and then we compute its flow features. We may introduce some temporal modeling. For example, we consider actually 3 types of temporal granularity. We consider video level, clip level, and segment level. We cluster the features using k-means. And then we use an appearance network, so a separate network, that is the bottom row that you see over here, to predict those pseudo labels with the appearance model. And in this way, we train on a large scale data set like kinetics. We train a self-training approach that we can then use in downstream tasks. And important to note that there are 2 different models at work here. So we have the motion pseudo label generator trained in step 1 that we use to extract motion features from the source set. And then we have an RGB appearance network that we use to predict the pseudo labels. And note that the network architecture of those 2 models can be different, which is a big advantage. Now, then for downstream tasks, we have a target dataset in which we want to recognize or retrieve something. We compute again appearance features only. We apply the self-trained model, RGB model, and with some class labels, we fine-tune this for the task at hand. And notice now that for these downstream tasks, there is no need anymore to compute optical flow while still having the benefit of motion augmentation. So this is the basic model for motion fit. A few implementation details. So in our experiments, we use UCF 101 and HMDB 51 for step 1, so training the pseudo label generator. We compute TVL1 optical flow, and we choose the R2+1 backbone, which is an efficient implementation of 3D convolutions. And why UCF and HMDB? They are both too small for direct training of a 3D CNN on RGB only. Essentially, training a model directly on the RGB pixels gives you too little data to build a reliable model that will generalize well. Now, for self-training, we rely on Kinetics 400. So we again extract the TVL1 optical flow, or we just rely on the RGB pixels. For the motion features, we use the same R2+1 backbone. And for RGB, we vary between either the R2+1 or the S3D-G model, which is also an efficient variant of a 3D convolutional network. And we test again on UCF 101 or HMDB 51 for the downstream tasks. Now, I will present some ablations to support the design choices of the motion fit model. And first, we investigate what is the benefit of relying on the motion representation. So here we train the pseudo label generator and directly apply it on, in this case, UCF 101 action classification to show the benefit of having a motion representation over an appearance representation on small scale video datasets. Now, as you can see here, when we train on RGB, the top 1 accuracy is close to 60, independent of the clip length. And when we do the same for motion, it increases with more than 30%. So really, flow is really informative for small scale datasets. It's a much better choice than appearance. We also played around with the multi-clip loss, where we vary the number of clips per video to only 1 clip, which is the entire video. 2 clips is 2 halves, and so on, to find that we get a good trade-off for 3 clips per video in our loss. And it further improves over a video level, the traditional video level loss. Then we looked into the benefit of this motion representation when doing the self-training. So we trained 2 different models. One is the pseudo labeler is trained on appearance information only, and the downstream task is again action classification on UCF. That gives us a top 1 accuracy of 74.5. But if we train the motion pseudo label generator on motion features, and so the features that we use as input for the self-training are motion features, we get a big jump. So we get 85.2 top 1 accuracy. And notice that during inference, both models rely on appearance information only. So at testing time, you don't need to compute flow, but the one model is injected or is augmented with flow information and the other one is not. And this is a clear benefit to augment your features. Then we also ablated the importance of the temporal granularity. So we compared video level with two recent segment level approaches, and these segment level approaches sort of like advocate a semantic partition of the video. So depending on the content of the video, they separate it into multiple clips, whereas our clip loss simply separates it into 3 equal length pieces. What we find is that this clip level has slightly better characteristic, is also cheaper to implement and much more efficient, and always improves over video level only. So that is convenient too. Then we looked into the impact of the number of clusters during pseudo labeling. Turns out that the number of clusters is not so critical. The amount of data that is available during self-training does matter. So if you compare the top row with the bottom row, the one is the Kinetics 400 validation set, the other one is the Kinetics 400 training set, which is basically 5 times larger. And you can notice that that has a good, a positive effect on downstream task results. So motion fit is not so sensitive to the number of clusters, but it does profit from more data during self-training. Then we did a bunch of state-of-the-art comparisons, and the first one compares motion fit with alternative knowledge transfer methods. So most notably the MERS and MARS approaches from the work from Crosto et al. And using the same backbone, number of frames, and resolution, we get a much better result than those two methods. And what is very interesting is that we even outperform alternative approaches that use 2D CNNs plus additional ImageNet labels. So motion fit efficiently uses the available amount of labels and outperforms alternative approaches. The next comparison is comparison against self-supervised action recognition. And we all use the same amount of labels here. And the comparison is quite involved because many papers use different backbones, slightly different settings in the number of frames that are being processed at the same time, resolution of the input frames, what types of modalities are being used, and so on. We try to group them here into multimodal approaches that either use visual and audio or visual and text, or vision-only approaches. And what we can see here when you go into detail in all the numbers is that motion fit does a good job and is best for the vision-only approaches, at least at the moment that we submitted the paper. I'm pretty sure that by now there are even better approaches. We are also on par with most multimodal methods. So using flow is competitive with alternatives using visual and audio. And quite likely, if you combine flow again with audio, you can get even more improvement. This is another task. Here we do self-supervised clip retrieval. So this is a common problem that people in self-supervised learning literature use to demonstrate their effectiveness. And again, we compare here in green with the visual-only approaches and in blue the multimodal approaches. And again, we are best for vision only and on par with the multimodal methods. And if you compare with identical settings like the backbones of Benaim et al., the SpeedNet, if I'm not mistaken, we really do much better with the recall at 1 of 31.6, where they score 13, and also for recall at 5 and 20, we are really much better. Here are some success cases. So the query on the top row is shaving beard, and it shows a keyframe representative of the particular query. And the goal is then to find the most similar videos in the test set, ideally corresponding to the same label. So only the video is provided and the label is used for evaluation. And as you can see here, that most results in the top 3 are indeed similar. Now, good for us, but what is more interesting is to look at the failure cases. Because here you see 2 failure cases, one for UCF 101 and one for HNDB 51. And although the results are wrong, it does preserve the distinctive motion patterns, right? It only uses RGB as input, but somehow the representation has captured characteristic motion, and it triggers on these characteristic motions. So if you see the table tennis shot, it sort of corresponds to tennis swing and bowling in terms of poses and body motion. So the representation is really augmented with the motion. I think that is the key benefit here, although that is sometimes also results in mistakes, of course. So first conclusion on motion similarity and motion fit. It transfers motion similarity to an appearance network in a very efficient way, because it does not require the costly optical flow computation during inference. And it is very well suited for deployment on small-scale video datasets with compute budgets, also on mobile devices, for example. That is part 1. The second topic I would like to address is audio-visual similarity. And this is joint work with Yunhua Zhang, Ling Xiao from the Inception Institute of AI, and myself, that appeared at CVPR this year. So here we look into repetitive motion, and repetitive motion is everywhere. It does not only occur in sports, but also in music, in urban environment, in natural environments, and really sort of like capturing these repetitions is sort of like an appealing topic. And we were not the first to consider this topic. Many actually have looked into repetition estimation in the past, so in more like classical computer vision works, where people have looked into signal processing based on Fourier analysis, but also using wavelets, for example. And these early works had to pre-assume a rather closed world setting. This was posing the problem and demonstrating the abilities of computer vision. So they had to assume a static and stationary video, for example, to estimate their repetitions. But static and stationary video is a very inapt assumption for the open or real world. So here you see a person in a kajak trying to pedal, and all of a sudden there is an acceleration by the person performing the activity. And with a standard Fourier signal, you cannot capture this acceleration. So together with Tom Runia, former PhD student, we have looked into this as well. We came up with wavelet transforms, so still sort of like traditional signal processing techniques, but wavelet transforms on the optical flow features as a reliable indicator of repetition estimation. And indeed, we demonstrated that this could handle also non-stationary world assumptions. Then, soon afterwards, at CVPR last year in 2020, 2 papers appeared that really advocated a deep learning-based solution. And well, deep learning is data and label hungry, so they could only demonstrate their point by introducing 2 new data sets. So folks from DeepMind introduced the Countix dataset, in similar spirit to kinetics, but then counting the repetitions in a short clip. And other researchers, Zhang et al., introduced repetitions for UCF 101. So they added the repetition annotations to UCF. And both datasets are available online. But there are some open world challenges that are unseen during training of such approaches, and I'm going to show you some videos. So here the quality of the input video is rather low, rather bad quality, so it's very hard to do accurate repetition estimation. This is very dark, and then there's also disturbing light in the pixels, so this makes also the recognition very hard. This is a very interesting one. All of a sudden, the actor that is part of the main repetition disappears out of the field of view. So this happens when you're considering real-world video. This is another challenging scenario, severe camera viewpoint changes. So how to count the repetitions in such a setting. And here there's a really messy and crowded environment. You don't know where to look. This is a scale change. So while there is a repetition, also the scale changes. So the pixels change a lot. So really challenging. And here there's really fast motion. So it's hard to keep track of the number of repetitions that are actually happening in the video. Now, we have come with a solution that essentially looks at video repetition estimation from a new perspective, because we do not only consider the computer vision aspects, the sight, but we also take into account the sound signal. And because there is often a clear correspondence between the sight and sound, there is a similarity that is a very effective means to estimate repetitions, as we will show. Now, as we were the first to rely on sound for this particular problem, we also proposed a first audiovisual model that has a sight and a sound stream, and each of those predicts is able to predict the number of repetitions, and we also have a new fusion scheme, so to say. In addition, we also add two new sight and sound datasets for video repetition estimation. Now, in general, the model works like this. So we have a sight stream on top that is composed of an S3D net that predicts the counting results per input clip, and also predicts a repetition class. This repetition class does not have a name. It's also not needed. It's a hyperparameter to identify how many repetition classes are needed. But it ties the repetition estimator on the perceived repetition class. For the sound stream, is essentially following the same tactic, but here we rely on the ResNet 18 using the spectrogram as input, and it also predicts the number of repetitions per repetition class. Then what is special about this model is the temporal stride module. And what this does is that based on the audio and visual features, it selects for each video the best sampling rate. So depending on the amount of activity, the number of repetition, it adapts the stride to make a better prediction. And then last but not least, we have a reliability module that decides what prediction to use. Sometimes you want to rely on the visual information, and sometimes you may want to rely on the sound information only. And we have a module that predicts this at testing time. So these are the basics of the model. When you go to the nitty-gritty, it is slightly more involved. I'm not going to go over all these details. You can find them in the paper and in the source code that we have also released. Okay, then we took the Countix dataset from DeepMind, and we created two more partitions based on their idea. The first one we call Countix Audio Visual, and this contains about 2,000 videos covering repetitive activity categories with clear sound and without background music, with a different training validation test partition. And the other one is what we call Extreme Countix Audio Visual. And this one is composed of 156 most challenging videos from Countix AV that we supplement with 58 other videos from VGG Sound dataset. And in this dataset, the sight conditions are basically too poor for counting, and they are intended for testing only. So this is really a real-world video AI test case, so you wish. Be it is a bit biased towards audio. Here are some samples from the datasets we are using, together with their counting results. I will show more results in a bit. First, some ablation on the benefit of the different components, and here we report mean average error. So the average error per video clipped, averaged over all the clips in the test set. The lower this number, the better. So if we only consider our side stream, which is already by itself able to predict repetitions, we score a mean average error of 0.33. Much better than the sound stream, which by itself is okayish but not super good. It scores 0.38 approximately in terms of mean average error. And when we add our temporal stride module, it goes down. Simply taking the average of the sight and sound, which is sort of like a traditional fusion method, further reduces the error. But if we use our full sight and sound model with the reliability estimation module enabled, we get the best overall result. So all the modules matter, so to say. This is a state-of-the-art comparison where we compare with existing papers. And what is interesting to see here is that our sight-only model is already good by itself and essentially state-of-the-art on several data sets. But when we combine sight and sound, we can really get the best possible results on all data sets. So you can argue that Countix is vision-oriented. Countix audio-visual is half-half, and Extreme Countix AV is more audio-oriented. Now, I think this is an interesting finding, maybe the most interesting finding of the work, where we consider the open-world video challenges on this Extreme Countix AV dataset. And we have sort of divided the test set into multiple vision challenges like camera viewpoint changes, cluttered background, fast motion, scale variation, low resolution, what have we. And we compared the sight-only model, the sound-only model, and the combined model. And what we observe here is that sound is less sensitive than sight for these vision challenges. And combination of the two always outperforms sight only. So it is really beneficial to add sound information to repetition estimation when it is available. And I have now the same video that I showed previously, but with the audio enabled. I hope this is audible for you guys. So the sound is really clear. You really hear the tennis ball pop on the racket. So that is the repetition cue. The pixels are challenging, but the sound is again very characteristic. And the actor may disappear, but the sound prediction is pretty good. So on the right, we see the sight and sound predictions together with the ground truth. Camera viewpoint, no problem. The sound does not care. Cluttered, but the ball makes identifying sounds. So sound can play a vital role, especially under harsh vision conditions. I think that is the bottom line. Now, I think I have only a few minutes left, so I have to go over this paper rather quickly. And here this is again from CVPR this year, together with Pengwan Yang and Pascal Mettes from my lab. And we look into the problem of few shot classification, but maybe I'm going to skip those. And our goal is basically this. So given a few trimmed support videos without any label temporal boundary annotation or box annotation. All we require is that they have something in common, in this case, ice skating activity. So we only require that in the query, in the support videos, the input videos have something in common and they are all trimmed. Then our approach can identify, based on this spatiotemporal commonality, it can identify the enclosing tuplet in an untrimmed query video. And the beauty, I think, of this algorithm is that there's no need for any label. So the only requirement is commonality at input time. So to give you some example of what this means, so here we have a number of support videos of somebody doing a skateboard activity. And now in a test video, we want to predict, localize the boxes. And in blue, you see the one-shot prediction of our algorithm, and in red, the 5-shot prediction. So the more examples it sees, the better the prediction will be. We use the transformer for this paper. I won't go into too much detail, but we adapted the transformer architecture for the particular problem. And the most important innovation here is this common attention block that really finds the commonalities between the support videos and the query videos. And we demonstrated it works also in noisy conditions, favorable to others. Here's an example again of showing it at work, and what is also of interest is that we also do it per pixel. So although we identify the tuplets in the end, we can also, inside each bounding box, we can also identify the segmentation of interest. So input, unlabeled, trimmed videos that have something in common, and at test time, it can identify the activity that the input videos have in common, and it can even identify the pixels belonging to the activity. Again, some results. And that brings me to the conclusion, exactly in 45 minutes. I think real-world video understanding with limited supervision is a grand challenge. Motion, audio-visual information, and spatiotemporal similarity are keys to address it. So you don't rely less on the supervision. They are all naturally embedded in modern learned representations. And we really have only started to explore the opportunities for real-world video AI. And with that, I would like to thank you for your attention.